This webcast continues in Worksheet 8E and looks at the last two problems, 11 and 12. Okay, in problem number 11, we're talking about a moon launching system that would have a magnetic rail that shoots items into orbit around the moon. So it would almost be like a big cannon kind of thing, only it would be powered by magnets. And so we'd have something that shoots stuff and kind of like a cannon, and it would launch them into orbit above the moon's surface. They're giving us the gravitational field strength of the moon, because remember, acceleration due to gravity on the moon is smaller than on Earth, and also the orbital velocity for that altitude. Okay, so at position A, we have something that's not moving, and it's on the ground, on the surface of the moon. But at position B, we have something that is moving in orbit above the moon. Okay. So if we think about the types of energies that were, the mechanical energies, gravitational, kinetic, elastic, and dissipated. And I'm just going to set myself up by putting those labels on both sides here. That way I've got reminders for what kinds of energies we might want to include. Let's see. It says, hint, consider the system to be the capsule and the moon, but not that rail gun that's going to shoot the capsule into orbit. Okay, so at position A, the capsule doesn't have any gravitational energy. It's on the ground, right? And it's no kinetic energy. It's not moving. There's nothing in this system that has the ability to store elastic potential energy. Okay, so there's no real mechanical energy at the beginning. But at the end, it says that it's at an altitude of 1,700, or I'm sorry, it's moving at 1,700 meters per second, and it's high above the Earth. It's 100 kilometers above the Earth's surface. Those are what I was looking for. So it is very high, and it is very fast. And let's see, does it tell us anything about friction? So I'm going to say no friction or air resistance. Well, there wouldn't be very much air resistance because we're on the moon. There's not much of an atmosphere there. But they're not giving me any information, so I'm just going to assume there is none. And so I've got gravitational energy, and I have kinetic energy at the end. Where did that energy come from? Because that's more energy in this capsule moon system than we had at the beginning. Some energy must have been transferred in. And it's being transferred in because that magnetic rail has applied a force that has made the capsule move. That was work. The process of work was done that transferred energy into our system. And that work equals the change in the gravitational energy plus the change in the kinetic energy of the capsule. Okay, and so now, let's see, are they asking me a question here? How much energy would be needed? This question of how much energy would be needed, that's basically saying how much work, right? The work was the energy that was transferred into the capsule system, so I'm going to be solving for that work. And I need to bring in my formulas to calculate each type of energy. Gravitational energy is mgh. Kinetic energy is half of the mass times the velocity squared. Let's see if we can find all these numbers here, and as we find them, we need to make sure they're in standard units. Okay, The mass of the capsule I see is 10,000 kilograms. G, we're not on the Earth. It's not 9.8, but they gave it to me. It's 1.6 newtons per kilogram. And the height is 100 kilometers. Uh-oh, that's one of the ones that we have to transfer or convert. 100 kilometers is 100 times 10 to the third meters. Okay, so plug that in, and then I'm going to plug in over here the same mass, 10,000 kilograms. The velocity is 1,700 meters per second. Okay, so in case it wasn't clear, I'm going to be solving for this work because that was the energy that had to be transferred into the capsule system. Okay, let me plug all these things in. We get a big number. It is 1.605 times 10 to the 10th joules. Okay, let's go on and look at the next problem, number 12. This is an interesting one. It says you're driving your car and another car cuts in front of you. So you have to apply your brakes, and your car leaves a 26-meter long skid mark while it slides to a stop. And the police officer gives you a speeding ticket, says you must have been exceeding the 15 meter per second speed limit. You've got the car's mass. There's a little bit of information here that is we have not really learned how to use, so I'm just going to go ahead and do this. The force of friction here, let me just calculate it for you. It should have been given to you. It would be the weight of the car times that 0.7. And so the force of friction here is 9,535.4 newtons. And that would be given to you on any of our tests or anything. It should have been given in this problem, so I'm sorry about that. Okay, so let's start looking. Our system here, they don't really tell me, so I'm just going to assume it's the car and the road and the earth. At position A, you're moving, right? At position B, you're stopped. And so let's think about what kind of energy this system has. There is nothing elastic here, so I'm not even going to put the elastic in my headers. Okay, so at the beginning, the car is moving. However fast it is, it's moving, it's moving. So there's kinetic energy. It's on the ground the whole time, and they're not talking about the height changing, so I'm not going to deal with gravitational potential energy. At the end, the car is stopped. It's not moving. It's still at the same height, but that energy has gone into friction, and or to overcoming friction, and so we have dissipated energy. So our conservation equation is that the change in the kinetic energy equals the change in the dissipated energy. Okay. And the question is, do I deserve the speeding ticket? The real question here is, what was the initial velocity? If we were going less than 15 meters per second, then we didn't deserve the speeding ticket. But if we were going more than that, like the police officer thought, then we do deserve the speeding ticket. Okay, but I'm going to find the kinetic energy as half the mass times the velocity squared. And then the dissipated energy is the force of friction times the path length. Okay, so the mass of the car is 1390 kilograms. I'm going to solve for this initial velocity. I know he thinks we were going 15 meters per second, but I'm going to check that. Right? I'm going to solve for this initial velocity at position A because I want to know whether or not I deserve the speeding ticket. But the force of friction is 9535.4 newtons. The path length is the length of those skid marks. We were skidding for 26 meters. And, okay. And as I've been plugging in, I've kind of been thinking to myself, are these in standard units? And they all have been. We didn't have to do any conversions. I'm going to solve for V. Let's see what that initial velocity was. So 9535.4 times 26, that's the dissipated energy. I'm going to divide by a half, and I'm also going to divide by the 1390. And so I get that V squared is 356.72. I'm going to take the square root to find V, and I get 18.887 meters per second. So yes, I deserved the speeding ticket.